Okay, so the first thing I want to talk to you about in physics is models and a few other things that we need to cover. First of all, what we do in any problem is that we take a simplified version of it, because if we took every detail into account, it would be hopelessly complicated. We could not put the math to it, nothing would ever get calculated. So, for instance, if we analyze the motion of a baseball throw, we could consider a lot of things. The ball is not perfectly spherical, rigid. It has raised seams that would increase air drag. It spins through the air. One of the big considerations is wind or air resistance, and sometimes it's absolutely fine to disregard it, and sometimes it's not. Quite often we do disregard it. The Earth rotates beneath the ball. As the ball changes its distance from the center of the Earth, its weight is going to vary. There are just so many things that you could take into consideration, and it would just be too much, hopelessly complicated. So, if we include everything, then we couldn't do the math. So what we do is we create a model of the problem, and we call the object in motion, a ball, a particle. And we neglect air resistance quite often. We make the ball move in a vacuum. Now, sometimes we will not neglect air resistance because at some point, for instance, when we talk about terminal velocity, air resistance plays a big part. But we overlook a lot of these minor things to talk about short term, or short range, like a ball being thrown. And those are perfectly valid assumptions to make. Something to think about, Galileo said all things fall at the same rate. Well, do they? If you're at the top of a tall building and you dropped a bowling ball or a feather, well, what kind of thing would we have to take into consideration? And of course, the answer is air resistance. So sometimes you do have to take those things into consideration, but quite often you can neglect them for minor things like a ball being thrown or dropped or that kind of thing. Okay, the other thing that we sometimes do, now a lot of our problems, they'll give us exact measurements and that kind of thing, but if we're measuring something in lab, or if we go to Valley Fair at the end of the year, Mall of America, we take some very rough estimates because it's too costly, too time consuming, maybe too dangerous to get up and measure how tall a Ferris wheel is or something like that. But these rough estimates can still be useful in giving us information, and we can look at our results and say, hey, were these good assumptions that we made, or were these good estimates that we made? And those are things that you discuss after the lab is run. The nuclear physicist Enrique Fermi called these things back of the envelope calculations. Just roughly, what is this? What do you think you could get when you multiply these or divide these? So what we're going to do in class, and maybe you could think about it a little bit ahead of time, is let's say you're writing an adventure novel and our hero escapes across the border with $1 billion worth of gold in a suitcase. And depending on the price of gold, the density of gold, is this even possible? And again, you're not going to have to be too accurate about this. You can do a lot of estimating. A lot of the things we do in physics is units, and we focus on those units a lot. And this is so different from what you have been used to in your education so far, and it does take a little time to get used to that, focusing on the units rather than the numbers. I mean, the numbers will come along, we'll put those in the calculator, but we really need to focus on the units. And like I said, that is so different than what you've been doing up to this point that I do want to spend a little time talking about it. You can read through here about what the International System for Time, what is a second defined as, and you can see that we've gotten more and more accurate and precise about what we're talking about as a second. Length as well used to be 1/10 millionth of the distance from the North Pole to the equator, and you can see how it's changed to be more and more precise. The mass, again, it is actually, I think that used to be, it is right now, based on the mass of a platinum iridium alloy in Kempton, Paris. Okay, I put this in here because when we are converting from one unit to the next, it's going to be dimensional analysis. And that's going to be really important in chemistry and physics. We want to make sure we know exactly what we're talking about as far as the units are concerned. So I'm going to try this. And when you're doing this, if you want to change from a nanometer to a meter, let's say that you have 5 meters and you want to change to nanometers, what we're really going to do is just talk about the fact that 10 to the negative 9 meters is 1 nanometer. And I just did a little bit of dimensional analysis. So that's what these equalities are referring to. And when you put this is really important too, we'll go over it in class as well, but when you put this 10 to the negative 9 in the calculator, and your scientific calculators, and I do recommend you use a scientific calculator versus say your phone, even if the app says scientific calculator, I would, the TIs are just much better. I would absolutely put this in. This number is 10 to the negative 9. Put this in and put in 1. Hit your EE key. You have to go second function. EE key and hit negative 9. Don't try to do the times and the 10 and the caret. That's really just going to get you in trouble. So do it this way. Here's some equalities that you can take a look at and refer to, and you can always look those. Okay, the other thing that we're going to talk about, which kind of annoys people, and we don't always stick with sig figs, and I know that it's kind of hard to stick with the sig figs, but let's go over the rules, know what they are, and we'll try to stick with the sig figs, at least to some extent. Okay, we don't have to be perfect. The whole point behind significant figures is that measurements always have uncertainties. If you use a regular ruler, you might be able to record the measurement. The thickness of your book cover is maybe 3 millimeters. It would actually be wrong to record that as 3.00 millimeters unless you used a caliper, a very expensive measuring device. So actually a regular ruler you probably could do a little bit better than 3 millimeters, but my point is that the measuring device is going to determine how many significant figures you record. We can indicate the accuracy of a measured value, how close you are to the true value, by writing the number and symbol and plus or minus. So you're within that amount. Okay. We also use significant figures to indicate the uncertainty. So the 2.93 millimeters, if I measure it and I'm recording significant figures correctly, it means that the 2 and the 9 were measured with the measuring device markings, but the 3 is an estimate. So all of these digits are significant. It just means that that 3 was an estimate. So for instance, if you had a ruler, we don't have a lot of room here, but and you had this. What you're basically saying here, if you were to say this is 1.123.5. So you go 1, 1, and then you have a marking right there that would indicate 3, and then right there is an estimate. So you say 1.5 maybe, or 6. That estimate is also significant, however. When you use measurements to calculate something, you have to make sure you round those answers so you incorporate this uncertainty. So in your calculator, of course, you're going to get all kinds of numbers. You are going to get the whole screen full of numbers. However, what you have to say is, well, what did we start with? What kind of measuring device was used first of all? Was it a ruler? Was it a caliper, a very expensive measuring device, very accurate? Based on those measurements we looked at in the previous slides. What are we looking at here? And then secondly, how did I calculate those? Did I multiply them? Did I divide them? Did I add? All right, well, the rules to tell how many significant figures are in a number is in Appendix P on page A1 in our physics book. There's also a little trick I want to show you with the Atlantic Pacific rule, which is just kind of a silly little way to tell how many significant figures. When you do scientific notation, only the base number determines the sig figs, not the times 10 to the x part. If you have counted numbers and those in equations, those we don't worry about sig figs. So for instance, if I say there are 10 people in the room, that's pretty accurate. I'm counting 10 people. It's not, there's no uncertainty there. Also those in equations, so if I say that an inch is 2.54 centimeters, that just, we don't even worry about sig figs with those. If you are the one measuring, then use all the markings on the device plus one more estimate. So just like what I showed you yesterday, or I mean in the last slide, you use those markings and then one more estimate, and that's significant too. And you can't go beyond that, obviously, but that just use one estimate. Once you know how many sig figs are in a number, you calculate and round to the right number of sig figs for your answer. I'll show you how to do that. As far as finding out how many significant figures are in a number, look at that number. This is a little Atlantic Pacific trick. Look at the number, see if it has a decimal point or doesn't. Okay, so it's either yes or no. If it has a decimal point, you say it is present, we're going to go to the Pacific side of the number. So if you think of the map of the United States, and I know that's not really a map of the United States, but I'm not very good at drawing in Michigan and Florida and Texas and stuff, so you know, this is our map. So if the decimal point is present, we start with the left side of the number here, the Pacific side. And what you do is you just go to that first non-zero number and count from there. And, you know, ignore the decimal point. So for instance, I'm going to give you an example. Let's say that is 0.0021 inches. Okay, so decimal point's present. I'm going to go to this side of the number. I'm going to go the first non-zero number, which is the 2, and I'm going to count from there. 1, 2. This number has 2 significant figures. Now, I can also do this. This is another example. Let's say I have 2,000 point. Okay, they put a decimal point there to indicate that it's exactly 2,000. Decimal point's present. I'm going to go to this side of the number. I'm going to go the first non-zero number, which is the 2, and count from there. This has 4 significant figures. Now, if it doesn't have a decimal point, let's just talk about the number 2,000. No decimal point. The decimal point is absent. I'm going to start on this side of the number. I'm going to go the first non-zero number, which is 2, and count from there. 1. This had 1 sig fig, whereas that has 4 sig figs. And the reason being is that there's a decimal point there. That's indicating to you that they are very confident in that 2,000. Whereas this 2,000, what they're basically saying is, yeah, it's about 2,000 feet away, something like that. That's a very rough estimate. Okay, when you do calculations, you're going to make sure when you do multiplication and division, 3.45 times 2.8 equals 9.66. Okay, and you have to round that. You get that in your calculator, 9.66. You must round that to 9.7 because the 2.8 only had 2 sig figs, so my answer can only have 2. That's the same with division. You look at all of your numbers, what is the weakest link? For addition and subtraction, you look at the places after the decimal. It's very different, really. So here I've got 3.45. I have 2 places after the decimal. I have 1 place after the decimal. I put it in my calculator and get 6.25, but since 2.8 only has 1 place, I'm going to round that to 6.3. Now, it's a very different rule than the multiplication, division, and we'll talk more about that in class and have you practice. Okay, so why don't you go ahead and do some examples here, and again, we will talk about them in class tomorrow. See what you think. Okay, dimensional analysis, I think I'm going to save for a different video. So I think I can only do 15 minutes. So I'm going to stop here. I'm going to use dimensional analysis for the next video, and so stay tuned.